Okay, so for the second part of this session on DeepQ learning and how to get there, what we are going to try and do is to implement DeepQ learning. So there are a lot of steps to get there. It's possible that we won't have the time to exactly do that in 2 hours, but at least we are going to give you all of the tools that are necessary to get the implementation working. So first off, I'm going to make sure that you all have access to the collab. So I'm going just to quickly issue a poll so that you can tell me whether you're able to download the collab that you can see on my screen. So you can get it on the GitHub. If you're not getting it on the GitHub, but just following the link, please do copy the notebook and do not edit directly the notebook, because if you edit directly the notebook, then basically you're going to modify it for everyone. And I'm just going to wait for mostly everyone to have access to the code book in order to start. Okay, so we have 10 people who currently don't have the notebook. Can those 10 people try to get it? And once they get it, just answer with A. Okay, so the numbers are increasing. I'm just going to give you a quick overview of what we're going to do. So this whole tutorial is an adaptation of a much wider and longer tutorial that you can find following the link that is in the notebook, and that goes through many more RL algorithms than the one I've presented here. In this tutorial, we are going to use quite a bunch of libraries that are quite common in reinforcement learning or in deep learning in general. So probably the less common one is ACME, which is a library which is going to enable you to tackle RL problems a bit more efficiently, a bit more easily. So basically what ACME does is it provides an interface for agents, which is going to make it easy to basically run agents against different environments. Then we are going to use JAX and IQ, which are mostly libraries which are used to build neural networks and to provide automatic differentiation capabilities, which is key to implementing deep RL algorithms, since most of what we are going to do is just about building neural networks and backpropagating gradients through neural networks. And then we are going to use DM environment, and DM environment is just a wrap around environments to provide a standardized API for environments. So once you have the collab, you can run the first few cells. And so first off, you need basically to connect to a collab instance, and you are going to need to run the first few cells basically just to do the correct installation. So install all of the packages that I mentioned and then import them. And once it's done, we are going to dig in the environment part of the practical. So we have a fair amount of people that have now access to the notebook, not all. Once you get access to the notebook, perform the installation. So now I'm just going to end this poll and start the second one. And for the second one, you're just going to tell me whether you were able to run the installation and the imports. So answer A, if you were able to run the installation and the imports. Answer B, otherwise. And if you're not able to run either of these, you can of course try to ping the TAs, which might be able to help you. So again, you need to run everything inside of Colab. So for the environment that we are going to use a very simple environment. And here I want to make a quick disclaimer. So we are going to implement deep learning, which is quite a heavy algorithm, and an algorithm which uses function approximation and uses neural networks to build its function approximation. And here we are going to tackle very simple grid world environments. On those grid world environments, you of course don't need to use deep reinforcement learning techniques. And on those grid world environments, in fact, you could simply resort to very simple finite state reinforcement learning, and things would work well and would probably work much better than with deep reinforcement learning. So here we're really trying to kill a very small fly with a huge chainsaw. So if you're faced with those kinds of problem in your day-to-day life, you probably don't want to use DQN to solve them. Here we're using DQN, but that's just to show you how to implement it. So the environment that we're tackling, just to give you a quick reminder, in reinforcement learning, most of the time what you are going to have an agent which interacts with the environment. So the interaction process will happen in this way. So you have the environment which sends an observation and a reward to the agent. The agent observes the observation and gets the reward. And in response to that observation, the agent is going to issue an action, and this action will modify the state of the environment. So here, typically, what is going to happen is that the agent is going to move in our small grid world, and by moving, it's going to modify the state of the grid world in the sense that basically the position of the agent, which is a variable of the state of the environment, is going to be modified by the agent moving. We are going to use two different versions of this very simple grid world. One version which is super simple. You have an agent which is above an object, and the agent just have to go to the object. So you can basically just follow a straight line and then go to the left at the very end. And we are going to have a slightly more difficult version of the environment where the agent has to navigate between two objects before reaching the reward. And of course, we are going to be able to test our implementation on both those environments. So if you have the collab, if you were able to run the previous cells, you can now run the first few cells of the environment. And this is going to give you a representation of the grids of the simple grid world environments and of the slightly harder version of the environment. So as I said, in this environment, what the agent is going to be able to do is it's going to be able to move and to move in the 4 directions. And the way the agent is going to receive reward is basically it's going to receive a positive reward when it gets to the object, and it's going to receive a negative reward when it bumps into a wall. So you get a reward of -5 when you bump into a wall, and you get a reward of +10 when you get to the object. And we're also going to have a discount factor here. The discount factor is quite important. If we did not have a discount factor, then basically the agent wouldn't be incentivized to go to the object as quickly as possible. And so the discount factor here, we're going to set it at 0.9. One interesting piece of information: in most RL environments, the higher you set the discount factor, the harder the environment, the more long-term your agent is going to have to behave in order to get maximal reward. So if you were able to run the previous cells, now you can run the next cell, which is about the specification of the environment. So the specification of the environment is going to tell you what each of the components of the environment is going to be. And all the components of the environments are going to be the observations, the actions, and the rewards. And here, basically, the observations are roughly going to be simply a grid, which is going to give you the state of the grid world with the position of the agent. You are going to, for the action, the specification of the action, so the action is just a discrete number, which goes from 0 to 3 included, and which correspond to the action that you are issuing. So 0 is going to be up, 1 right, 2 down, and 3 left. The reward, but as is the case for most reinforcement learning environments, is just going to be a scalar, and the discount is also going to be a scalar. Do note that we're also providing a discount information in those environments, which means that with the DMN API, you would be able to have discounts which changes in the course of interacting with the environment. And after analyzing the specs of the environment, we are going to reset the environment. So that is, we are going to put the environment in its initial state. So basically, we are going to reset the position of the agent, and then we are simply going to plot this initial state. And by plotting this initial state, we are going to be able to have a look at where our agent is compared to where our object is. So I'm just noticing the contrast of the plot is not exactly optimal, but if you squint at the grid, you can see that you have one tile where you have the agent and one tile where you have the object. But since it's black on purple, it's not really visible. So we still have 29 people which were not able to run the environment up to this, to run the collab up to this point. If by any chance you were able now to run the environment, please press on A so that we can know that you're not struggling anymore. And for the others, you can go through to the end of the environment parts of the notebook. And so now we are going to get to the interesting part. So here we had the environment, but we are providing the code for the environment, because basically it's just a lot of boilerplate and of logic, which is not necessarily super related to the reinforcement learning to the implementation of DQN. But now we're getting to the implementation of agents. And so to make this implementation a bit easier, we're going to use ACME, which provides an API for agents. So an API for agents is simply a set of functions that agents should implement. So I encourage you to go have a look at this API and to try and understand why it is the way that it is. And the different functions that the ACME API is going to give us are functions which are going to allow you to both pick actions, which is the main thing that agents are going to do. They are going to interact with the environment by picking actions. And the second part is they are going to learn from the observation and the rewards that they are receiving. And to do this, ACME provides two things. It provides an observe method. The observe method allows you to take into account the fact that you just received an observation, and an update function. And the update function is going to be used to update the internal state of the agent. So typically in a deep reinforcement learning setting, updating the state of the agent mostly mean updating the parameters that the agent is maintaining, and typically updating it using gradient descents. Actors, so agents in Acme, the main class that we are going to use for agents in Acme is the actor class. And this actor class, so it has the three methods that I just mentioned. It also has an observe first method, which specializes the observe method, but for the first observation in an episode. Because most of the time you don't want to consider this first observation as you would any other observation. So as I said, take a detailed look at the API. And once you've taken a deeper look at the API, basically we're providing you two functions to be able to directly use the API to interact with the environment that we've provided. And those two functions so are run loop and evaluation loop. The run loop, what it's going to do is it's going to run the environment with the agent and make the agent update its internal state as a result of the interaction that it has with the environment. And then the evaluation loop, it does the same, but it does not update the state of the agent anymore. So you can have a very quick look at those two functions, the functions implementing the run loop and the evaluation loop. And once you've done that, we are going to go to the first exercise, which is going to be about implementing a random agent in Acme. So random agent is just an agent which, whatever the state of the environment, is always going to return a uniformly random action. So a uniformly random action which is selected among the four actions which are at the disposal of the agent. And so in this random agent, of course, we are going to have to implement all of the methods which belong to the actor API, that is the select action, the select action method, the observe first method, the observe method, and the update method. So maybe just to give a bit more information. So on each of those methods, we've typed them. So we've given types to each of the elements of the method. So the select action method, as you would expect, as was depicted in the first little schematic, the agents issues an action as a reaction to an observation. So quite naturally, the select action method, it takes as input an observation. And the way Acme is treating observation as nested arrays. And nested arrays, so don't be afraid of this type. It's just a nested structure. So a nested structure, typically, imagine that as being a dict of dict of dict of dict of tuples and of lists. So a composition of the basic types of Python. So dictionaries, tuples, and lists, and also name tuples that can be arbitrarily nested. But in our case, mostly our observations are either going to be simple NumPy arrays, or they are going to be dictionaries of NumPy arrays. So don't be too bothered by this types.nested array thing. It's just that in more complex environment, typically you could have access to different modalities of observation, and in that case, the observation would probably be more complex than just one NumPy array. Then for the observe first method, you're receiving a time step. And a time step, what it is, it's a named tuple which contains different information about what just happened in the environment. So typically, it's going to contain an observation, it's going to contain a discount factor, it's going to contain a reward. So as we were previously mentioning, basically, this observe first thing, what it should do is it should just tell the agent, okay, you just, the environment was just resetted, and here's what the first step of the environment looks like. And this first step mostly contain an observation, but also contain other information such as the reward and the discount factor. And similarly for the observed method, except that this observed method also contains an action, which can be useful if you want to maintain the action of the agent as an additional internal variable for your agent. And finally, the update function. So the update function does not take as argument anything useful for you. So basically, the weight variable, we're not going to use it in this tutorial. So the update function is going to modify the internal state of the agent, but it modifies it purely from what the agent has previously observed. Okay, so I'm going to issue another poll, and in this second poll, you are going to tell me, so whether, first off, a first poll to tell me whether you were able to run the notebook up to this point. And secondly, I'm going to issue a second poll after the first one where you are I'm going to monitor where you are in the execution, in the implementation of this first exercise. And once we reach a decent amount of people which have successfully answered to the first question, we are going to provide a detailed solution. Okay, so we have a fair amount of people that have at least run the notebook up to this part. Now, I'm going to end this first poll, and then the second one is going to be about whether you were able to successfully answer the question. And I did not mention it, but of course, once you've implemented your random agent, you can test it. Even though testing it might be a bit of an overstatement, you can simply check that it runs by running the cell which is just below the solution cell. And once it runs, it at least tells you that you correctly implemented the API. But it does not verify that the action that you are inputting are actually uniform. So just as a very small hint, but I'm also pretty sure that most of you don't need it. In the agent, we're already providing you the number of possible actions that the agent could try in this environment in the form of the num values attribute. So you can directly use this num values attribute.
In the meantime, do you mind answering a question?
No, of course.
So there is a question that asks, if there's no action, what do you observe then? Maybe I missed a part of the explanation. I don't know exactly what he's referring to.
Oh, so maybe the person would have to tell me if I'm correct in understanding the question. But if that's if that's about the observe first thing, basically at the first step of the environment, so you haven't done anything at all, and you're just placed in the environment. Before doing anything, the environment has to give you the information of the first frame. So typically, if your environment was an Atari environment, the first observation would be the first frame of the game before you did anything at all. Does that answer the question? And then for all of the other observe, basically you are going to have you are going to act before the observation, and so you can also get the action that you performed before getting the next time step.
Yeah, I think he says that he's referring to the very first observation.
Okay.
Okay, thank you very much. Yes, that's perfect. Tak. Oh, and somebody was asking what's the poll for. I guess he missed it. He missed the question.
So the poll is for whether you were able to answer to solve the first exercise, so to implement the random agent.
All right, thanks. Okay, so there is some feedback. Somebody's asking if there is possible there is an error, and some other people are indeed giving feedback. Testing phase with attribute error. Random agent object has no attribute environment spec.
It's not entirely impossible that I did a small. So if you have this problem, what you can simply do is start off the random agent. But I think, yes, in the solution you might have it. You can do self.environment spec equal to environment spec, or just remove the self.environment spec in the line self._num values equal to self.environment spec. So if you can all see my screen, you can simply remove this part here, and this should work.
Yeah, okay, awesome.
So to the question, do we need to implement just select action or everything? So you need to implement everything because your API requires you to implement everything. But basically, just a hint, the other methods are quite simple.
Okay. I didn't get why the shape of the observation is 3-dimensional. The first 2 dimensions define the size of the grid, whereas the 3rd dimension for.
So if I recall correctly, basically the 3rd dimension is a channel dimension. So we're not giving the state of each tile as an integer. We're giving it as a one-hot. So basically, for each spatial location, you get a 3-dimensional vector. And this 3-dimensional vector is going to be 1, 0, 0 if you are a player. If in this specific tile of the environment you have a player, it's going to be 0, 1, 0 if it's a wall, and it's going to be 0, 0, 1 if it's the object. Does that make sense?
Yeah.
I maybe messed up the number. The correct one-hot vector for each of the different for players, walls, and objects could be shuffled, but it does not matter a lot.
Okay.
Okay, so I guess we have a fair amount of people that actually at least tried to do this exercise. So I'm going to give a quick solution. So as I was mentioning, basically, this exercise is pretty simple. You just, in the select action, the only thing you need to do is use NumPy to pick a random value between 0 and your number of possible actions. So we're simply going to do this in the solution, simply using NumPy to generate your action. And then for all of the other methods, you can just use pass to say that those methods are not going to do anything. In a random agent, you don't want to update the state of your agent, so you can directly use pass. And that's it for the random agent. If you implement it that way, things should run in the test cell. Are there any questions on this random agents, things that you did not understand? I'm going to...
It's not on the random agent. There's another question that popped out though, which is how do you specify the end of an episode if the agent never reaches the goal?
So the way you specify the end of an episode, so in the time step variable that the agent gets when it observes, you have, so in next time step, you have a field of next time step, which is step type. And in step type, you are going to receive either step.first, step.mid, or step.last. And if you get a step.last, you know that you are at the last step of the environment. So basically, you know that after this step, the environment is going to be resetted. And if you have an agent, basically for most of the environment that we are using, what people tend to do is after a certain number of time steps, you force a reset of the environment. You don't let the environment run forever.
Okay, thank you.
So if there are no more questions, we are going to move on to the next part of this practical, which is going to be a bit more oriented on deep learning and how to use JAX and IQ to build deep learning model and then to backpropagate through them. So if you may not be familiar with JAX. It's not super widespread at the moment, but it's a pretty nice library. And the idea, so we're first going to concentrate on JAX, and then we're going to go to IQ, which is roughly just something on top of JAX, which is going to allow you to simply define neural network architecture using JAX. And so if you're not familiar with JAX, what JAX is, it's a numerical computation library, much like NumPy, but it gives you access to a couple of things that NumPy does not give you access to. Typically, it gives you access to specialized hardware, so it allows you to use either GPUs or TPUs. And also, one thing that we are very interested in deep learning, it gives you access to automatic differentiation and a couple of other facilities. So at very first glance, JAX looks a lot like NumPy. So if you've already written NumPy before, you are going to be quite you're not going to be extremely frightened by what basic JAX is doing. It basically, what you are going to do is you are going to take your NumPy function, replace it by a JAX.NumPy function, and it's going to work out of the box. So at first glance, if you know NumPy, you know JAX. Now, there are a couple of difference of JAX compared to NumPy when you want to start doing things such as differentiating functions or making functions run efficiently on specialized hardware. And we're going to go a bit more in the details, but the idea is that JAX takes inspiration from functional programming. So one of the core citizen of JAX code are pure functions. I'm just going to make a quick poll here about how many people here know what a pure function is. So A is going to be, I know what a pure function is. B is going to be, I don't know what a pure function is, compared to an impure function in functional programming terms. Okay, so we have a wide majority of people which do not know what a pure function is. So a pure function as compared to an impure function. So when we are doing math and not computer science, we're always defining functions, and those functions are exactly what we are going to refer to as pure function in computer science. So a pure function is simply a function such that if I apply twice the same function on the same arguments, I'm going to get exactly the same value. So in maths, that's always the case. In computer science, that's not always the case, because we have nasty things which are called side effects. And side effects are things that modify the context in which a function is called and make it so that if I call the function twice, then maybe the context has changed between the two calls to the function. And so the function is not going to give me the same kind of answer after the first call and after the second call. So here I'm giving you two examples, one example of a pure function and one example of an impure function. So the first example of a pure function is something very simple. It's a combination of an hyperbolic tangent function with a linear function, and we're dividing the hyperbolic function by a quadratic function. But the idea is here, as soon as I specify the x arguments of the function, then I know that there is a one-to-one mapping from x to the answer of the function, and I can change completely all the variables which happens outside of this function. This function is always going to give me the same output if I give it the same input. So this is a pure function. Now, there are a lot of impure function in computer. Let me share again. Okay, now you should be able to see it again. So yes, I'm talking about this pure function here. Now, there are a lot of places in computer science where impure functions happen. And typically here, I'm giving you an example which is encapsulated in a very small class, which I'm going to call the counter class. And the idea of the counter class is that it's going to define a counter, and then it defines a method for this class, which is going to use this counter and update this counter each time the function that it defines is called. And basically here, the unpure function, so it's not unpure, it should be impure function and not unpure. But the results of this function is going to change. Even if I don't modify the input to this function, the output of the function is going to change after each time I call the function again. So the first time, basically, I is going to be 0. So the result to a call of impure function on any kind of variable x is going to be hyperbolic tangent of x. The second time I call the function, it's going to be x plus hyperbolic tangent of x. The third time it's going to be 2x plus hyperbolic tangent of x. And so this means that I cannot simply rely on the function to tell me to have an input to output mapping. So after those explanation, again, another poll about, did you understand the difference between pure and impure function? Just that I know, okay.
Well, the answer, somebody asked, what's the difference between an impure function and a random function as a family of random variables indexed by the state space?
So a random function would be impure, because if I call the function twice in a row, basically the random state, the random number generator of the computer is going to be modified from the first to the second call. So random function are impure function, but not all impure function are random function. Typically the one with counter, there is nothing random about it, but still it's an impure function. So you have one inclusion, but not the other.
Okay.
So one majority of people who now understand what a pure function is, and now I'm going to be able to tell you why it's important to use only pure function in JAX. So when you're using JAX, always try to think, are the functions that I'm defining pure or impure? If the functions are pure, you're good to go. If the functions are impure, then at some point you may have a problem. And the idea is that once you've defined a function in JAX, what you can do is you can do a lot of different operations on this function. Typically, you can use a grad operation. And what grad is going to do, so I have my function, I call JAX.grad on this function. This is going to return me another function. And this function, instead of giving me the value, the output of the initial function as its output, it's going to give me the gradient of the input function as the output. So here in the collab, I'm giving you an example. So I had my pure function, which was, as I said, a combination of numerical operation. I call the JAX.grad functor on it, which returns a new function. So grad pure, now it's also a function. So it's going to take exactly the same thing as pure function as arguments, but it now returns the gradient of pure function instead of its value. And then I can call it on any point. And I'm going to get, so if I call pure function, I'm getting the value of pure function. If I'm calling grad pure of x, I'm getting the gradient of pure function at point x. And so this is super useful. This is the way that JAX is defining, is providing automatic differentiation facilities. And now you can also see why it's important for your function to be pure in order to be able to call JAX.grad. So I'm going to go into a bit of detail here, which is not necessarily completely useful, but may help you in understanding what's happening and why you need pure function. When you call JAX.grad on pure function, what is going to happen is that JAX.grad is going to look at the code of your pure function. It's going to completely process your pure function in symbolic terms, and then it's going to, from the code of your function, is going to output a code which is going to be the code to backpropagate through your function. But to be able to run this, it has to be sure that the function, that there is no nasty things that happen outside of the function, no nasty code that happens outside of the function, which is going to modify what the function is doing. So basically, JAX.grad is something that in spirit acts on the code of the function. So if the code of the function is not self-contained, you have pieces of code which are outside of the function, which acts on what happens inside of the function, then basically you're not going to be able to call JAX.grad. The reality is a bit more complex than that, but that's the rough idea of what JAX.grad is doing and why you need a pure function to be able to define a gradient. As a side note, this grad function, it only works when you're outputting a single scalar. So if you're outputting typically a vector or a matrix, JAX.grad is not going to work. And it's going to output an error saying JAX.grad only works with scalar outputs. So this JAX.grad function is super useful. Now you have, JAX provides other functors, other operators which act directly on functions for other facilities. So typically, JAX provides a facility to automatically vectorize function. And when I'm saying vectorize function, basically you have a function that takes a scalar as input and outputs a scalar, but you want to apply this function element-wise to a vector. Then what you can do is just define the function that acts, that takes one element as input, use JAX.vmap on this function, and now you automatically get a function that takes a vector and outputs a vector. So typically, if you wanted to have a tanh function, imagine you had the tanh hyperbolic tangent function, which was only usable on scalar inputs. You could directly obtain a function that works on vector inputs by calling the JAX.vmap of jnp.tanh. And this would give you a tanh that works directly on vector. Of course, you don't need to do this for tanh because tanh already works on any kind of inputs. But if tanh was only working on scalars, then you would have to do something like that. So typically one of the useful things that you can do with VMAP is if you have an operation that does matrix multiplication between a matrix and a vector, and instead of having one matrix and one vector, you have a batch of matrix and you have a batch of vector. And what you would like to do is multiply each vector in your batch of vector by the corresponding matrix in the batch of matrix. Then what you can do with JAX is simply you are going to define your matrix multiplication as you would usually do, which takes just a matrix and a vector, and then VMAP it. And when you VMAP it, the operation that was acting on one matrix and one vector now acts on a vector, on a batch of matrix and on a batch of vectors. And that's exactly what we are doing in the next cell. Basically, we're taking the usual matrix multiplication of NumPy, and we're extending it to work on batches of matrices. And so this is going to do kind of element-wise matrix multiplication. One small thing that you may have seen in this example, and that is very related to one of the questions that we had previously, is about how JAX is handling random numbers. So as one of you was asking in his previous question, all stochastic functions, so all functions that involve random numbers, all those functions are impure. They are impure because basically the random state of NumPy or the random state of Python is modified each time you call a random function. And so if you call a random function twice in a row, the result at the second call is not going to be the same as the result at the first call. And we know that JAX is not able to handle it. If we try to do this in JAX, JAX is not going to be able to understand what you're doing. And typically, when you try to take a gradient of a function which is stochastic, it's going to fail, or it's going to not give you the proper value. So to circumvent that, what JAX is doing is, instead of passing random number implicitly as Python does or as NumPy does, so basically you would have a global random state, and this random state is modified each time you output a new random variable, a new random number. What JAX does is it maintains those random state explicitly. And so you are going to, when you want to access random numbers in JAX, you are going to first define a random number generator, which is something you can get out of jax.random.prng key. And then you are going to pass this RNG directly to your JAX function. And when you pass this RNG directly to your JAX function, you can then call any kind of random function and pass as the first argument this RNG. So for example, here I'm trying to generate normal numbers out of a random number, normal numbers, basically to be able to apply my batch matrix multiply. The way I'm doing it is simply as the first argument of my random function, I'm passing the random number generator. And if I want to get a new random number out of my random number generator, I have to split my generator. So basically, each time I'm going to call to use this random number generator, I need to instantiate a new random number generator. But since I don't want to have to set the seed for all these random number generators, what I'm going to do is I'm going to take my first random number generator and just split it in as many parts as I want random numbers. So for example, here I have a single random number generator. So typically I could use only one random number. I could get only one random number out of it. But what I can do is, if I want two random numbers and not only one, I'm going to first split this random number generator into two, and then call one instance of normal with the first random number generator, and the second instance of normal with the second random number generator. Okay, so that's pretty much it for the basics of JAX. Of course, if you want to learn a bit more about it and feel more confident about it, there's a lot of documentation around all this. And typically, I advise you to read in a bit more detail the page that I linked at the end of this section, which is JAX the sharp bits, which explains in much more detail how to handle random number generators and why purity is important for JAX. And now we are going to go to the exercises, where the first exercise that we are going to try and solve, I'm giving you a function, which is typically a scalar function, which just compute the square of your input number. And what I'm asking you to do is I'm going to give you a vector of numbers, and I want you to evaluate using JAX the derivative of the square function for each of those number in inputs. So typically, if I have 10, 20, 32 as my input, I want to first evaluate the square function on 10, 20, 32. And then for each of those elements, I want to take the derivative of the square function on this input and give that as output. And so you may think, okay, it's going to be trivial. I'm going to take my function and just apply grad to it. The problem is, as I was previously mentioning, grad only works with scalar outputs, and if you're giving a vector to your function, it's going to output a vector. So you're not going to be able to directly call grad on this function to get what you want. So same as before, I'm going to issue a poll, and as soon as you think you have the correct answer to this batched gradient, just press A on the poll. And of course, you have so you have the implement cell to implement your solution, and then there is a test which is going to check whether your solution is correct or not.
All right. So while they work, there was a question. It was on what you said previously, and it's what's the difference with the np dot seed of my seed? I'm not sure the difference with what, because it was what you were talking about before.
So I think the difference is the difference between NumPy the NumPy seed and JAX handling of random numbers. So the idea is when you're changing the seed in NumPy, you're actually effectively.
Oh, it appears that you're lagging. Is it only on my side to the other panelists? Okay.
No.
All right. Okay. Luckily, it happens in a moment where everybody is busy doing exercises, so we can wait for a few minutes while Corentin solves his connectivity issues.
I'm sorry, I lost my connection.
No problem. No problem. It was the right timing since everybody was working anyway. You were saying about the NumPy seed?
Yes. So yeah, the main difference is NumPy seed is global, and it's defined for any random function that you are going to use. The NumPy the JAX seed is local, and you have to add it to each of the function that is going to use stochasticity to be able to actually use the stochasticity. So you cannot have a stochastic function in JAX that does not have an RNG as its argument. If your function does not have an RNG as its argument, it's not stochastic, and I know it.
All right, thank you.
So already a fair amount of people who have successfully answered the batched gradients question. So of course, there is a very easy way to implement this batched gradient function without relying on JAX facilities. Of course, I don't want you to do that. I want your solution to extend to any function that I could give you as input. So if your solution was just derivative function is equal to 2 times x, that's not what I want. And once you're done with this first exercise, you can go to the next one, which is mostly the same, except that instead of working with vectors, you're going to work with matrices. It's quite straightforward. It's going to be pretty much the same thing. And then a side question, even though you're probably not going to be able to notice it. So JAX also provides you with a function which is the JAX.JITE. which allows you to take a function and it's going to output a compiled version of this function, which should run much faster. So once you have your matrix function, your matrix gradient function, can you find a way to make it more efficient? And if you listen to what I said, it should be straightforward. So I'm going to issue a second poll for the matrix gradient question. I guess all of the persons that answered the previous question yes, people who solved the matrix gradient already solved the other one. So I'm just going to look at the answer to matrix gradients.
So there is a comment.
Yes.
That says that he thinks there is a third line missing in the implement code block. The code block that defines the JITed solution that can be tested.
It's very possible. It's very possible. Oh. Yes, I misnamed it. It should be JITed solution and not fast batch gradient.
All right.
Thanks a lot.
Yeah, you're welcome.
So you're doing nothing with fast batch grad. Instead of fast batch grad, you're implementing the JITed solution. So also a fair amount of people that have solved the matrix gradients. I'm just going to go through the first exercise, so about batch gradients and fast batch gradients or JITed solution. So it's super easy. Once you have your function, you first want to apply gradient to it. Since you know that your function is directly operating on scalars, you can call gradient on it, and it's going to give you the correct answer. That is, it's going to transform your function, which takes x and outputs x to the square, and is going to output a function that takes x and outputs 2x. And then, so this function acts on scalars. You can directly get a function that acts on vector simply by calling the vmap function on this gradient function. And once you get your vmap function, you can get the JITed version of this vmap function by simply calling JAX.JIT on this thing. So this might seem quite trivial, but in the context of deep learning, it's not as trivial as that. Typically, in many frameworks, it's quite difficult to compute the per batch gradient, the per element gradient of the parameters in a batch. And with JAX, it's completely straightforward. You just have to define the gradient for one element, you vmap it, and then you get the gradient for a whole batch of data. Okay, so are there any other questions on the batch gradient? No other questions, so we can go to matrix gradients. So matrix gradients, pretty much the same.
Sorry to interrupt you. One question just popped out at the last second.
Okay.
What is the at operator in JAX.vmap of lambda AB?
So the at operator is just NumPy, the NumPy matrix multiply operation.
All right.
It's an alias for np.matnull.
Got it. Thanks.
And so for the matrix gradient, it's going to basically be exactly the same thing as for the batch gradient. So we're going to take our previous JITed solution, we're going to vmap it. So this gives us something which, instead of working on vectors, now works on matrices. and then we can re-JIT it. So we had something which was already JITed, but having a JITed function and then vectorizing it, you're not sure that the code you're obtaining is optimal for the second vectorization. So you can call JAX.JIT a second time and get a more optimized version of your matrix gradient function. Of course, the correct thing to do would probably be to not JIT your first function. So use directly your first function in the second VMAP. So you would have two VMAPs in a row and a grad, and then JIT the whole thing. Because if you JIT the whole thing, basically the compiler won't have to undo the things that it did in the first JIT, potentially to better optimize your whole function. Okay, in the interest of time, I'm not going to do the batched indexing exercise that we have here. Of course, you can do it as a homework if you want. Even though this, and typically in RL, it can be quite useful to have this function that would be able to do multidimensional indexing in a tensor. And we are going to go directly to haiku. So the idea of haiku, basically, if you've done deep learning before, if you've worked with either PyTorch or with TensorFlow and Keras, or Sonnet even, basically haiku is the equivalent of Keras for JAX. So it's going to work pretty much the same. You are going to have kind of the same feeling with haiku as you have with Keras or Sonnet or PyTorch. You are going to stack up layers. You are going to have access to sequential operators, which allows you to have lists of modules and just stack them up. The only big difference is that when you're defining such modules, typically in PyTorch, those modules are going to contain their own weights. And the problem with modules containing their own weights is that when you are going to perform a gradient step on your module, you are going to change the parameters of your module. And then when you want to call the module again, and you're calling it simply with its inputs, you are going to have a computation that is going to depend on the state of the module. So if I have a linear layer in PyTorch, I can call this linear layer on an input X. This is going to give me one result. Then I'm going to do a gradient step on the linear module. This is going to change the weights, but it is going to change them implicitly. So I'm not keeping a variable which is going to be parameters and which is able to attest for this change of parameters. The change of parameter directly happens in the module. And then if I call module again on another variable X, it's going to give me a different answer than the first time, simply because the parameters of the module changed. And so we don't want to do that in JAX. We want to only have pure functions. The problem is, if we want to have pure functions, then we need to maintain our parameter argument to all the functions that are going to implement simple neural network operation. For example, to call a linear layer, I would have to call linear of parameter of my linear layer and inputs to my linear layer. And this is going to become quite cumbersome quite quickly. So what haiku is doing, it's allowing you to define impure functions in the form of modules. And then once your impure functions are built, it's going to allow you to call a functor which is going to take your impure function and turn it into a pure function. And this pure function, in turn, is going to take as input both the parameters and the inputs of your network. So an example is probably much simpler than all the nonsense that I've been telling you. So here, I'm doing exactly what I was mentioning. I'm defining a linear layer in haiku. And as I said, it's pretty close to what PyTorch or Keras would be doing. To define a linear layer, I'm just calling the iq.linear function. And a slight difference between iq and PyTorch is that in iq, you only mention the output size. You don't mention the input size. So once I have this linear layer, so as I was telling you, this linear layer, there is a problem. This is not a proper pure function that can be used with JAX, because the linear layer, it has a set of weights, and this set of weights, it appears nowhere in my easy linear net function. So I need to make those weights explicit. And the way I'm doing this is I'm taking my easy linear net function and I'm passing it through an hk.transform. And the role of hk.transform is to take an impure function, transform it into a pure function that now takes as additional input the parameters of my neural network. So this hk.transform, I'm a bit lying to you. It's not only transforming my impure function into a pure function, it's transforming my impure function into two pure functions. It's transforming my impure function into one function that allows you to obtain the initial parameters of my linear layer, and a second function that takes as input the parameters and the input of my network and give the output. And this is so because to be able to obtain, to be able to evaluate my linear layer, I need its parameters, but to get its parameters, I need something to initialize my layer. And so once we've transformed our function, we're going to do exactly what I said. So first initialize the layer, and that's what we're doing in the next cell. We're calling easy linear. So easy linear that I've defined in the previous cell, it's now a named tuple which contains two fields. It contains an init field and it contains an apply field. And the init fields, it takes as input a random number generator and an input to my function, and it outputs a set of parameters. And of course, so this is a very simple example of what I was mentioning earlier, that all stochastic functions in JAX require a random number generator. Here, to generate my first set of parameter of the linear layer, this set of parameters most of the time is going to be something which is stochastic. So calling it twice should give me two different answers. And so in JAX, since I don't want to have this impurity of stochastic function, I'm giving as additional input to my init function a random number generator. And so once you've executed this first comment, you get a set of parameter, and you can inspect what this set of parameter is. And basically, this set of parameters, it's going to be what you expect it to be. That is two different sets of weights, one set of linear weights and one set of biases. And once you get those parameters, you can directly use them to apply your linear function. So you are going to call the easylinear.apply, which are going to take as input the parameters of the function. It's also going to take as input an RNG. So this RNG here is useless because the linear layer, it's not a stochastic layer, but hk.transform is going to assume by default that all functions that you're using are stochastic. You can, of course, remove this stochastic part by mentioning in your hk.transform, I don't want any stochastic argument for my apply function. So it's taking parameters, RNG, and the input to your linear layer. And then once you've applied your linear layer, you get its output, and you can directly print your outputs. And then, so now you have only pure functions. Apply is a pure function. Init is a pure function. You have a set of parameters. You have sets of inputs. You can directly define your loss function on those parameters and those inputs, and take the gradient of your loss function with respect to any parameter. So by default, JAX.grad takes the gradient with respect to the first set of parameters, but I can also mention that I would like to have the gradient with respect to the third set of parameters, which would be x. and JAX would as easily compute the gradient with respect to the input and not the gradient with respect to the parameters. So all is good now. We're going to have a couple of exercises here. And first off, we are going to try and implement a linear regression using the linear module that we've just defined. So the idea is pretty simple. You're going to define your loss function. You're going to take this loss function and apply one of JAX transformation to get not only the value of your loss function, but also its gradient. And then you're simply going to use this new function that you've defined to be able to perform gradient steps, which are directly implemented. And here it's a very simple SGD that is implemented. So the whole training loop that is implemented in linear regression shows you how to do stochastic gradient descent in JAX. So here it's not stochastic because we're doing full batch gradient descent, but you could of course apply it to stochastic gradient descent. I'm going to issue a new poll. On which you are going to be able to tell me where you're at in this exercise. And in the meantime, we're going to answer more questions.
All right, awesome. So first question is it possible to solve the matrix VMAP problem using the in-axis and out-axis parameters to only call it once?
Yes, definitely. So in-axis and out-axis, what you could do is simply call JAX.VMAP and VMAP on the two first axes. So by specifying in-axis equal 0, 1 and out-axis equal 0, 1. And you would get directly the matrix gradient operation.
Great. Second one.
It's probably just an abuse of definition. I'm calling them functors because they take as input functions and output functions. But I don't think they are actually functors in category theory.
Okay. And what about the torch and n functional? Are they pure functions?
So I would have to look back at what torch.nn.functional does. The problem is in most torch code, you're using, as soon as you're using torch.module, you're doing something that is impure. But I think that all the things that are in torch.nn.functional are actually pure functions.
Okay.
Still, you wouldn't be able to use them with JAX simply because JAX only can operate on NumPy operation and not on torch operations.
Okay, great, thanks. So last one. I'm pretty sure this is the case, but just to confirm, the JAX grad function computes the gradient numerically, right? If so, how can we get estimation of the error of the value returned by JAX grad?
So I'm not completely sure about what you want to say by computing the gradient numerically. So the way JAX.grad computes the gradient is really it's going to inspect your code and perform backpropagation on the code. So basically, it takes the code and outputs the code which should be equivalent to performing backprop. So you know that if you have a computational graph, by reversing this computational graph, basically you can get the computational graph which corresponds to computing the gradient of the function you were previously defining. If by numerically computing the gradient you mean it's doing finite error difference to compute the gradient, then no, it's actually looking at the code and looking at the computational graph and performing backprop on the computational graph. Now, if you want to get an estimation of the error the value returned by JAX.grad, I think in most cases you can be quite confident that it's given you the best estimation of the gradient that you could use. Now you can still compare the results that JAX is giving you to the actual finite difference value that you would get by simply evaluating the function twice with small distortions of parameters.
Okay, that's great. Thank you very much.
So of course, if you want to know more detail as to how JAX is actually doing these things on the code, it's pretty simple, and it's quite close to what PyTorch is doing, except that it's doing it directly on the function at the moment that it's calling JAX.grad. So at the moment where you're calling JAX.grad, what JAX does is it's taking an abstract array, which is an array that has the same shape as the array you are going to actually put into your neural network or your function. It's going to take this array, forward it through your code, by doing that, it's able to build the computational graph of your actual function. And then when it gets the computational graph, it can basically just compute the computational graph, which corresponds to backpropagating through the initial graph. And that's also what PyTorch is doing, except that PyTorch is doing it every time you're doing one forward computation and one backward computation.
All right. Thank you very much.
So we have less and less people participating in the polls. I think it's related to the fact that we're getting close to noon.
Yeah.
Okay, I'm going to give the solution to this exercise now. So defining the loss function is quite easy. Basically, it's just... Oh, I'm not sharing. Easy. Basically, once you have your linear layer, which is defined, you simply have to compute your mean square error between your predictions and your targets. So once, and this is going to give you the proper loss function to perform linear regression. Once you have it, you simply want to take the gradients, but this time you don't want to take solely the gradients. You want to also output the value of the loss as well as the gradient. And JAX has a function for that. So instead of calling just JAX.grad, we're going to call JAX.valueNgrad. And valueNgrad is going to output both the value and the gradient of the function. And to squeeze a bit of speed out of it, we're going to call JAX.JICE on the resulting function. And this way, we're getting a valueNgrad function, which is an optimized function, which takes as input the same thing that loss function, that is a set of parameters, an RNG, inputs and targets, and outputs the value of our loss function and the gradient of our loss function with respect to our parameters. And then to run our training loop, so to get the loss and the grad, we simply have to apply our valueNgrad function on the correct set of parameters using the current RNG. So this is not very important because anyway, our linear function does not use an RNG. But basically here in the code, what I'm doing is that at each iteration, I'm changing the state of my random number generator. And if I want to have random numbers which are correctly distributed, I need to do that. I never want to use the same RNG twice. Each time I call I use an RNG, I must use another one for the next stochastic call. And then performing gradient descent. And if you follow those steps properly, you should have you can execute this cell and you are going to have a loss function that goes down. Okay, so this is it for the linear regression. Now we are going to implement a second thing, which is we are going to implement a Convnet, which is going to take as input things that look like the observation of our environments and output something which has the same shape as our number of actions. So we are going to implement an approximate Q function. And then in our implementation of DQN, we are going to make use of this function approximation for our Q function. So let's get to it. So just as a reminder, our observation are 9 by 10 by 3 tensors, and we'd like to output something which is num actions. Of course, I'm forgetting the batch dimension here, but always consider that there is a leading batch dimension. Also know that IQ handles that by default. So IQ, the function that you get out of IQ always operates on batch of data. And I want you to implement such a Convnet. I'm giving you the exact specification of the Convnet. So from this, you should be able to completely implement it. And once you've implemented it, you can check that your Convnet is actually outputting something of the correct shape in the test function. So same thing, I'm issuing a poll and just tell me if you've successfully solved this exercise. So to solve this, you can, of course, use all of the facilities that IQ provides. That is, you can use conv2D, which gives you convolutional operations. You can also use sequential, that allows you to stack up different modules, and you can use the different functions that are provided by JAX.NN. Typically, you have a RLU function that is in JAX.NN, which you are probably going to find useful. And if you have any question, don't hesitate to ask. Okay, so this question is maybe quite simple. I could maybe give the solution just before the lunch break. So the idea is simply I'm going to stack up layers. So I'm going to use hk.sequential. In my hk.sequential, I'm going to first stack up a convolutional layer, followed by a ReLU layer, a second convolutional layer, a ReLU layer. And then, so at this point, I'm getting something which still has spatial dimensions. So if I have spatial dimensions, I can't directly apply an MLP on top of that. So I need to flatten my spatial dimension to get something which is simply a 1D, a batch time 1D vector of activations. And hk.flatten does exactly that. It flattens all dimension except for the batch dimension. And then on top of this flattened representation, I can directly put my MLP, which has a number of outputs, which is exactly the number of actions. Oh, but the lunch break is at 12:30, so we still have plenty of time. We still have plenty of time. Do we have any question on this Convnet implementation?
Not so far. It seems that you've been a great speaker and everybody's understanding everything.
No question. That's good. So now we're getting to maybe the trickiest part of this practical, which is about implemented DQN. So now we have enough to basically build our own neural network. We know how to differentiate it, so we can get access to the gradients of our Convnet, and we just have to place things in order to implement our own DQN. The first thing we're going to do is we're first going to check that we're able to run a DQN version that is directly implemented in Acme. So I'm going to ask you to have a quick look at the Acme implementation of DQN, and then simply to use this implementation to get an Acme DQN agent, and then to run it to check that you're getting some results. And once you've run it, you are going to be able to get some visualization out of your DQN agent. So go ahead, implement that. That's pretty easy. You just have to read the documentation of the Acme agent and then to simply call it. And once you've called it, so when you want to run it, you can simply you will have to run it several times in order to get a proper agent, an agent which is going to actually solve your task. And once you've run it a couple of times, you can visualize it, but you can also visualize it in the course of training. So the visualization are going to give you a notion of what your learned Q values are. And if you remember exactly what the environment looks like, basically the environment is you have your agent, which is above an object, and you're going to get a reward for getting to the object. So the idea is that your Q value is going to just become higher the closest you are to the object. And so that's what you should see in your learned Q values representation. And of course, so you have as many, you are going to have Q values for each state of your grid and each action in your action space. So the action that are going to have maximal Q values are always going to be the action down, because in this environment, for at least for the line which goes from the agent to the last goal, because the optimal policy is just to go down all the time. So same thing here, sharing a quick poll and tell me if you were able to solve this exercise. I'm leaving a bit of time here just to be sure that people have the time to at least read a bit the code in the Acme code base.
Seems like one question popped up, which is, could you repeat what the jax.random.prng key function is doing?
Yes. Okay, so the jax.random.prng keys, what it does is it takes a seed and give you one random number generator. And once you have one random number generator, you can start generating random numbers. So typically, if I want to generate samples which are distributed according to a normal distribution, I can take my RNG key. So I would first do RNG is equal to jax.random.prng key and specify a seed, say 0, and then use it to generate normally distributed samples, but by using jax.random.normal, specify the key equal to RNG, and then specify a shape, which would give me the shape of the number of samples that I actually want in my normal distribution. And this function is necessary because for each random function that you have in JAX, for each stochastic function that you have in JAX, you need to explicitly pass in the source of stochasticity, which is the random number generator. So this jax.random.prng key is what provides you the source of stochasticity for each of your functions.
Okay, thank you. Another one, does JAX handle other Python structure, such as dicts or others?
So I guess by that you mean, can I put in a dictionary as the argument of one of my function, and typically call grad on that function and get a correct gradient out of it? And the answer is yes for any nested structure. So if you have a dict, if you have tuples, if you have list, if you have named tuples, if you have composition of those things, basically if you have directed acyclic graphs, no, if you have just trees of those things, it's going to work. And typically if you call gradients on an input that is a dictionary, what you get as a gradient is also a dictionary. If you call gradient on something which on an input which is a dictionary of tuples, what you get as a gradient is a dictionary of tuples.
Okay, great. It seems like it was exactly the case he had in mind. Oh, or she. Oh, I'm not sure. So, thank you.
You're welcome. And just as a side remark, when we were doing this, when we in the last exercise, basically we were differentiating with respect to params, which were the parameter of a linear function, and those parameters are IQ maintains them as a dictionary of dictionaries. So directly here basically we were already doing that. And as another small side comment, in the last line of the linear regression exercise, basically we're doing a gradient distance step. Now we're doing a gradient distance step on something which is a dictionary of dictionary, and that's why I cannot directly use the minus operator between the parameters and the gradients. I need to basically go down to all the leaves of the trees and apply my gradient distance, basically my subtraction on each of the leaves of the trees. And that's why I need a JAX.tree multimap. JAX.tree multimap, what it does, it's simply, it goes to the leaves of the trees and it applies your operation on the leaves of the trees. And then what it outputs is an output that has the same shape as your initial inputs. Okay, so I think that we can get to the solution of the Acme DQN agent. As I was saying, this is pretty straightforward. This is just about pulling out the DQN.DQN class of Acme and then just providing it the correct argument. So there is a slight trick that we need to do here. Basically, Acme, what it requires is a function. It is an already transformed function and not directly your initial function. So you need to transform your network before giving it to Acme. And you need to do a second thing. So Acme doesn't use RNG by default. So you need to also remove the RNG from your transformed function. And to do this, you are going to call HK dot without apply RNG. And what HK dot without apply RNG does is for functions that actually don't use an RNG in their call, they remove the RNG argument from the apply function. Then we're just giving a couple of by default arguments. You could of course try to tune them to look at their effects on your training. And then once this solution agent is implemented, as I was saying, you can run it and get some visualization out of it. Okay, is this clear for everyone? If so, we can get to the actual meat of this part, which is about implementing your own DQN. So just to implement your own DQN, we are going to mostly follow the recipe that Bilal gave us to implement DQN. So we know that DQN, mostly what it's doing is it's implementing a regression problem between your current approximation of the Q function and some targets, which are just the application of the Bellman operator on a target network, on a target Q function network, which is from time to time updated to match your online Q network. So you have a couple of things to implement here. You have a loss function to implement. You have the update of your target network to implement. And that's pretty much it. These are the two main parts of DQN. So yeah, provide a loss function. Basically, we're providing the boilerplate code to actually update your Q function once you've defined your loss function, and then simply provide the code to actually update your target Q network when you have when you need to do it. So basically, after a few number of iterations on your data set. So the code that we're providing is quite simplified in the sense that many of the boilerplate is already handled, and we're splitting it into two parts. One part which is the DQN learner part, one part which is the DQN agent part. The DQN learner part, what it does is it mostly takes it mostly cares about the learning part of DQN, as the name kind of implies. The DQN agent basically provides the correct API to the Acme agent to be able to run as an Acme actor. Maybe, oh, and the last thing you need to implement is the initialization of your network. So here, one thing that you may want to do, or one thing that you will need to do, is that the network that your DQN learning is taking as input is untransformed. So you need, the first thing that you need to do in your initialization is to transform this DQN, network, probably to transform it without RNG, because you're not going to use RNG here. And once you've transformed it, you need to get a first set of parameters out of your network. And this you know how to do because we did it with a linear layer. So I repeat, the three parts that you need to implement: the initialization part of the network, then the loss function, and finally the update of the target network. If there are things that you don't understand in the code, don't hesitate to ask questions. And I think that's pretty much it. Maybe a very small note here. So your loss here, you are going to see that it depends on basically two sets of parameters: target parameters and online parameters. The parameters are of your current Q function approximator. And so this is pretty natural because you want basically to regress your online network to targets which are built using the target network. And one of the crucial things is that we are only differentiating with respect to the online parameters. We're never differentiating with respect to the target parameters. And the target parameters are updated in another way. They are basically updated by hard copying the weights of the online network to the target network from time to time.
So there is a small question, which is, can you explain what we see in the visualization part?
Yes. Okay. So maybe what I can do is run it. I should have done this from the beginning. Now it's going to be a pain to run it all. Yes. So it's necessarily going to crash, but I hope that by going over all the cells that actually crash, I'm going to be able to do something. So yeah, those visualization, they represent the value of your Q function approximator for the different actions. So for the action up, down, left, right, and for each of the states of the environment. So if we were in a tabular setting, basically our Q function would be a huge tensor of size number of states time number of actions. And basically what we are visualizing, for a fixed action, the Q for a fixed action, the Q values for this action, it's a matrix that has the same shape as your observation, because basically your observation consists of all the states that you have in your grid. And so you can directly visualize it, and you can see for each of your states, what is the Q value of the state for this particular action. So this roughly tells you what are the state in the environment that your algorithm, that your Q learning deem as good, and what are those that are considered bad. Those which are very light are good states. Those that are very dark are bad states. Okay, so we're running into problems here, but I don't need that. I'm going to execute this. Up. Not going to execute that, but I need to execute. I don't want to do this, but I'm going to get trapped somewhere. So let me just do a small patch to the notebook. Up. Need to execute that. Run this. Name agent is not defined. Yes, because it's called solution agent. We're getting there. Yes, now it's working. Okay, so now we get the visualization. So here the visualization are not necessarily super good, but that's because the agent was only run for a couple of steps. Let me run it for much more than that. No. Now it should be at least decently good. Not exactly yet. Let's have it run for a couple more steps. And let's increase a bit the number of episodes. And now we're getting something a bit better. But yeah, overall, what we're observing is basically, so you have to really squint to notice what I'm going to say. But here what you see is that your V function is basically quite high on things that are on the line between your initial point and your last point. And this is pretty normal, basically, because only those states correspond to the optimal trajectory. So when you go down those states, basically, you know that if you're following your optimal trajectory, you're going to end up in your goal state, in the state that is the object. And what you can also see, so here we're considering what we look at is a decently good estimate of the optimal Q function, but it has mostly, so now basically the data that you see mostly resemble data from the optimal policy. So you're basically never getting out of the path that go from the top, from your starting point to the final location. And so that means that for all the other states in your environment, you're going to get pretty bad estimates of your Q function because you're not getting there anymore. You're just following the optimal path. So, but still, what you can see is that all those other points are much lower Q values. All those other points, only the points on the vertical line have a high Q value. All the others have small Q value. And in the middle, you have the V function, which is just the average of your Q function on your policy. And what you can see is same. You have the same kind of idea that basically you're going to sorry. Basically, you're going to be better when you go. The more down you go, the better you are. So you need to squint a bit to see that the points at the very bottom are a bit lighter than the points at the very top, even on the line. But that's the idea. And so there is something which might appear strange to you, which is the fact that QS up is also quite high, while the hop action is never the correct one. The up action is always incorrect. Basically, each time you go up, you'd rather go down. But the thing is, when you're going up, you're back to a state where you are still on the optimal path. So since you're still on the optimal path, your Q value is still high on this element of the path, and so your Q value down is still up on this element of the path. And so since the QS up is mostly 0 plus gamma for QS down, then basically you're still getting a value which is pretty high and much higher than what you get when you look at QS right and QS left. I hope that was clear. If that was not, feel free to ask another question on that.
Okay, yeah, I guess it was. So thank you. And there's another one, which is, can we see the number or the percentage of times that each state action was visited?
So it's not implemented, but you can definitely implement it. You'll just have to modify a bit the run loop and the evaluation loop. So at the moment, it's not implemented. It's not super difficult to implement.
Okay, great. If I choose the root to be -1 at each time step, I should see up actions being darker.
So it's probably going to be a bit darker. So here, if you look a bit closely, your up action, your line on the up action is still quite a bit lighter than the vertical line on the down action. Now, even if you set your reward to -1, going up is still much better than going right or left according to your optimal policy. Because basically your optimal policy, you're still on the vertical line that goes from, that is on the optimal track. So even with a -1, you're still going to have the same kind of patterns.
Okay.
Of course, one other thing.
A question from the beginning. In the select action method of an agent, do we always return the index of the action instead of the action itself?
Yes. Yes.
Okay. There you go.
Let me see. Let me check that we're on the correct version or whether we are on the correct version or not. Let me check in agents. No, it's not the correct version. I'm going to try and grab it. Collab. I think the correct version was not saved. So what I can do is simply do the modification in place or mention all the modification that needs to be done. That's a bit of a pain because we did them yesterday, but I guess the collab is not very friendly to do those kinds of things.
Okay.
Oh, that would be super nice if we can send, yes, if we can send the version that Louis has written, that would be really cool.
Awesome. Yeah.
Thanks a lot, Louis.
You want to take this last question?
Oh. Yes, we can definitely do this. So what you can do is indeed increase the limits set in the environment. Now, I think even with this limit, if you run the environment for long enough, your agent should, in the end, succeed in getting to the reward. It's still a pretty easy environment.
Okay. And there's another one. What's the difference between the number of episodes and the number of steps in the DQN?
Yes, the number of episodes, it's going to be, so since we're, at least the Acme version of, if I recall correctly, the Acme version of DQN is asynchronous. What is going to happen is that you are going to execute your environment, and at the same time, you are going to have a thread, which is pulling data from your replay buffer and updating the queue function with respect to those data. And the number of steps corresponds to the number of gradient steps that you're doing on your replay buffer, while the number of episodes correspond to the number of episodes that you're doing in the actual environment. So there is one that is simply the number of episodes that you're doing in the environment. The number of steps would be the number of gradient steps that you're doing on your queue function. I could be wrong on that one. You may have to check in more details, but that's my intuition.
Okay. Yeah, okay. We will replace the notebooks later.
Yes.
Okay, so if you have any other closing thoughts, you, of course, feel free to.
So if there are any more questions on this practical, you can of course ask them during the session this afternoon. And maybe just to say that if you want to have a practical which is in the same spirit, but maybe longer and covering more algorithms, don't hesitate to have a look at the first link that is on the collab. And this is going to give you a much more in-depth practical, which covers a lot of reinforcement learning algorithms, going from very basic to a full DQN implementation.
Okay, so thank you very much, Corentin, for your amazing practical session. And
thanks a lot.
Yeah, it was great. And to all the other attendees, we will go on a lunch break. So we will all see each other at, if I'm not mistaken, 2 o'clock this afternoon. Yeah.
Thank you all for attending.
Yeah, thank you.